Okay, welcome folks. Today's lesson we're going to talk about measuring the rates of reaction, and you can see the little GIF that I've got on screen there. We're looking at a fairly violent reaction, A plus B plus C. Now it is important to note that not all reactions occur like that. Of course, some happen very slowly, like rusting and so on. In today's video we're going to look at how we would measure that. Okay, so just a little bit of a recap in chemical kinetics. Thermodynamics really asks the question, does a reaction take place? And then when we're talking about kinetics, kine meaning movement, from the word to mean movement, talks about how does a reaction proceed, the reaction mechanism, and then also how quickly does it proceed, and that is what we're going to focus on today, reaction rate. So the reaction rate is the change in the concentration of a reactant or product over time. And the units are usually given in moles per litre per second. So that big M concentration-wise in chemistry we've been talking about every second. So how is that concentration changing per second? So if we look at a reactant to product, where our reactants are in green, we can look at the rate of the concentration of the reactant over time. So the change in reactants over time, or we can look at the change in products over time. Now you'll probably notice on screen that the delta R, the reactant, is actually negative because of course the concentration changes, it diminishes or decreases with time. So that's important to say. So if we look at the reaction A to B over time, and we look at a graph that's produced here, again, we can look at it in two ways. We can measure that concentration over time. We can look at the concentration of A, or we can look at the concentration of B, being the product. Now, when we look at this graph, what we're starting to see here, hopefully what we're starting to see on screen, is a non-linear graph. So a non-linear relationship between those concentration or number of molecules over time. And it tends to be exponential curves that we see. So we're going to continue exploring that. So look at some examples here, reaction rates and some Stoichio. Some dinitrogen pentoxide decomposes to form nitrogen dioxide and oxygen gas. And we're given the rate of production of nitrogen dioxide, and we're asked to determine the rate of decomposition of dinitrogen pentoxide and formation of oxygen. So we need to get the rate of decomposition of that reactant and the rate of formation of the product. Knowing what we know, well, we can use stoichiometry, and we can relate the dinitrogen pentoxide to nitrogen dioxide and say that that is a 2 to 4 relationship, or a 1 to 2 in its lowest terms. And so we could just multiply that initial rate that we were given for nitrogen dioxide, and we could multiply it by a half, because that's the molar relationship, mole rate there. It is important to state that we should put a negative there as well, because it is the reactant, and that's going to get less over time. And we could similarly do the same for oxygen. In this case, we're multiplying by a quarter because that's the mole ratio. And note that the rate here is a positive, not a negative. Another type of question, what's the average rate of production of ammonia for the system between 1 and 4 minutes if the concentration, and you're given concentrations after various times? Well, it would simply be the change in concentration over the change in time. And that would be written as moles per minute. You could, of course, change that to moles per second as well. And so our concentration graphs would look like this. I just want to highlight, if you have a nonlinear graph and you want to get the instantaneous rate for any of these nonlinear graphs in science in general, what you would do is you would get the tangent. And the tangent is basically a line that's going to touch the curve once. So just looking on screen, the higher tangent is notified on screen. And once you have your tangent drawn, then you could get that actual rate. It would be rise over run as per usual. So how do we measure reaction rates? Well, there's many different ways that are shown on screen. One of the simpler ways is to measure the mass. You have your reactants in a conical flask on a mass balance, and you have some cotton wool at the top just to stop some spray loss, and the gas escapes, and you measure that mass over a certain amount of time periods. You could also measure the pH, and there's various other methods. We're going to just explain the other methods in more detail now. So we could measure gas volume. If the reaction produces a gas, then it's easy to measure the rate of reaction based on the collection of gas. So what we would set up is an apparatus like on screen where we've got the flask, we've got our reactants in, and we're basically collecting that gas, and the gas is going to push a syringe, and it will give us a reading on the syringe. We'll be able to calculate the amount of gas that's in the syringe by those notches, those graduations on the syringe. And if we were to look at a graph, you can see down in the bottom right, the green dashed line that I've put in here would be an example of a tangent at the very beginning. You can see it's a very steep slope, and that represents a steeper or a higher rate. If we look at the rate at the end of the reaction, just before it stops, we'll see that it's the red dashed slope. There is a much non-steeper slope. It's a much more gradual slope. That means it will have a lower value, a value reading for rate. So how do we measure conductivity? Okay, so if the reaction produces ions, and the conductivity of the solution will change. And we can measure that. We know that there's a relationship between ions and conductivity. It's the ions that allow conductivity to take place. And we could use something like a conductivity meter. There's many different varieties of that. You could, if you didn't have access to a conductivity probe, you could set up a simple circuit across the solution, and you could measure the conductivity using a multimeter or such apparatus or tool. And you would get a graph similar to one on the right of the screen. Notice the units for conductivity here on the y-axis. They're microsiemens per centimeter. And over time, again, we see this curve diminishing. And so this is basically saying that there's less and less conductivity over time in this particular instance. And this is for a saponification reaction. So the other thing that we could do is measure the color change. We could use something called a spectrophotometer, and you can measure the intensity of the color change. Now I'm just going to employ use of this PhET simulator, PhET simulator. They have fantastic simulators, and I'm just going to run this simulator and talk us through what we're looking at. So when we have the simulator set, we can, on the PhET website, you can press this wavelength generator. Notice we can also choose what's in the solution. I've chose potassium chromate. We can increase the concentration. Now you'll see as I increase the concentration, the transmittance, what we're seeing on the photometer, gets lower and lower. Also, if we increase the size of the solution, the test tube, the transmittance got lower and lower. How much this tool here was picking up got less and less. The percentage got less and less. So I would encourage you maybe to try that simulator. It's a very good way to have a look at that, and they look at different methods of measuring as well. And so that's basically it for today. We are hopefully a lot better in terms of our knowledge of how we would measure rates of reaction. And if you found this video useful, then please give me a wee thumbs up.